adjoint of a matrix. This would be very useful for a lot of calculations using matrices. Now let's say we have a matrix A. Let us say A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, or in general we can say Aij, which is a 3 by 3 matrix. Okay, so the adjoint of A would be, let's say, A11, A12, A13. Remember, here these are small letters, these are capital letters. A21, A22, A33, sorry, 23, A23, A31, A32, A33, and we take the transpose of this. That would be the adjoint. Okay, so in other words, this would be A11, A12, A13, A21, A22, A23, A31, A32, A33. Here, each of these capital A's, that is the cofactors, right? So this is a cofactor matrix. So Aij would be equal to minus 1 to the power of I plus j, because it will keep changing from minus to plus, and m of ij, where m is the minor of Aij, right? Lowercase ij. So if capital A11 would be the cofactors of this, that means A22 times A33 minus A23 times A32. So for example, A23 would be equal to minus 1 to the power of 2 plus 3, and the determiner, that is the determinant of the matrix, once you get when you remove the second row and the third column. So this would be A11, A12, A31, A32, which would be minus 1 to the power of 5 would be minus, and this would be A11 times A32 minus A12 times A31. Similarly, A12 would be minus 1 to the power of 1 plus 2, and the determinant of A21, A23, A31, A33, which would be again negative power, so minus A21 times A33 minus A31. This should not be a straight line, this should be a bracket. A31, A23. Yes, so that is the cofactors of lowercase 1 written as capital A12. So let's actually do a problem. Let's say A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Easiest way of writing a matrix. Okay, now what we'll do is, first of all, we'll find out the cofactors. So cofactors of 1, that would be what? That would be A11, which is equal to determinant of 5, 6, 8, 9, which is equal to 9 5s are 45, 6 8s are 48, which is equal to minus 3. Similarly, of 2, that is 1, 2 is equal to, that would be 4, 6, 7, 9. But remember here, minus to the power of minus 1 to the power of I plus j. So 3. So this will be minus. Here it was 1 plus 1. So plus. which is equal to minus 9 4s 36 minus 7 6 42, which is equal to minus 6, so plus 6 of 3. It would be A13 is equal to, again, minus 1 to the power of 1 plus 3, that is 4 E1, so plus, and this would be 4 5 7 8. 4 8 32 minus 35, which is minus 3. Okay, next is of 4, which is A21, which is going to be 2 plus 1 is 3, so minus this one, so that is this row, this column gone, 2 3 8 9. So 2 3 8 9 will give us 9 2s 18 minus 24, that is minus 6 minus 6, minus 6 times minus is plus 6 of 5, that would be A22, which is again 2 plus 2 4, so plus, okay, 1379, so 1379, which will be 9 minus 21, which is minus 12. Okay, so now of 6 is equal to A23, 2 plus 3 is odd, so minus, and this will be 1 2 7 and 8, which is equal to minus 8 ones 8 14, minus 6 minus is 6 of 7 is equal to A31, which is 3 plus 1 is 4, so 2 3 5 6, which is equal to 6 to 12 minus 15, which is minus 3 of 8 is A32, which is 3 plus 2 is 5, so minus 3 2. So this would be this row and this column one, so 1 3 4 6, so 1 3 4 6, which would be minus 6 minus 12, which is minus 6 times minus is 6, and finally of 9 would be A33 is equal to 3 plus 3 6, so plus, and this would be 1 2 4 5, 1 2 4 5, which is equal to 5 minus 8, which is minus 3. Okay, great. Now we have found the cofactors. Now what we do is we write it as a cofactor matrix. We write it in the matrix form. C is equal to, start off from 1, A11. A11 is minus 3, 6, minus 3, 6, minus 3. Then 6 minus 12, 6. 6 minus 12, 6. And finally minus 3, 6, minus 3. Now take the transpose of C, which gives us, in this case it's pretty straightforward, so we can very easily write the transpose is symmetric. Okay, so this is the adjoint of A. So adjoint of A is equal to the cofactor matrix, its transpose of the cofactor. Okay, so this is pretty straightforward, right? Let's do the adjoint of A, right? Given as 1 minus lambda, 2 3, 4 5 minus lambda, 6 7 8 9 minus lambda. We have to find the adjoint. Okay, we know adjoint of A is equal to the transpose of the cofactor matrix of A, right? So let's do that. So A11 would be 112, so plus, and this would be 5 minus lambda, 6, 8, 9 minus lambda, right, which is equal to lambda square minus 14 lambda plus 45 minus 48, which is equal to lambda square minus 14 lambda minus 3. Okay. A12 would be 1 plus 2 is 3, so minus, this would be 4, 6, 7, 9 minus lambda, which is equal to minus 30, 9 4s are 36, minus 4 lambda minus 42, which is equal to minus 6 minus 4 lambda, which is equal to 6 plus 4 lambda. Okay. A13 would be plus 4, 5 minus lambda, 7, 8, which would be 3 plus 1 4, so plus 4 8 32 minus 35 minus 7 lambda, which is equal to minus 3 minus 7 lambda. No, this way, since we'll be opening the bracket, this would become plus. This will become plus. Okay. Now A21, this would be equal to 2 plus 1 3, so minus 2 3 8 9 minus lambda, which is equal to minus 9 2s 18 minus 2 lambda minus 24, which is equal to minus minus 6, so plus 6 plus 2 lambda. Okay. Now A22 would be determinant of 1 minus lambda, 3 7 9 minus lambda, which is equal to this would be lambda square minus 10 lambda plus 9 minus 21, which will be lambda square minus 10 lambda minus 21 minus 12. Okay. Now A23 is equal to minus 1 minus lambda 2 7 8 minus 8 minus 8 lambda minus 14, which is equal to minus minus 6 minus 8 lambda, which is equal to 6 plus 8 lambda. Okay. A31 is going to be 2 3 5 minus lambda 6, which gives us 18 minus 15 plus 3 lambda, which is equal to 3 plus 3 lambda. No, this is going to be 12, not 18. So that means this will become 6 to 12. Okay. Now A32 would be 3 plus 2 is 5. So minus 1 minus lambda 3 4 6, which is minus this will give us 6 minus 6 lambda minus 12, which is 6 minus 12 minus 6, so plus 6 plus 6 lambda. A33 is equal to, now this would be 1 minus lambda 2 4 5 minus lambda, which is equal to 5 minus 6 lambda plus lambda square minus 8, which gives us lambda square minus 6 lambda minus 3. Okay, so we have got the factors. Now C, which is the cofactor matrix, would be, what is it? This is going to be lambda square minus 14 lambda. Lambda square minus 14 lambda minus 3. Then the next one will be A12, 6 plus 4 lambda. 6 plus 4 lambda. Next is minus 3 plus 7 lambda. minus 3 plus 7 lambda. Then A21, 6 plus 2 lambda. 6 plus 2 lambda. 2 would be lambda square minus 10 lambda minus 12. Then we have 6 plus 8 lambda. Then we have minus 3 plus 3 lambda. Then we have 6 plus 6 lambda, and lambda square minus 6 lambda minus this is our cofactor matrix. Now the adjoint will be the transpose of this. So let's write that. Lambda square minus 14 lambda minus 3, 6 plus 4 lambda minus 3 plus 7 lambda. Then 6 plus 2 lambda, lambda square minus 10 lambda minus 12, 6 plus, no, 6, yeah, 6 plus 8 lambda. Then we have minus 3 plus 3 lambda, 6 plus 6 lambda, and lambda square minus 6 lambda minus 3. So this is equal to the adjoint, right? Now this can be written as, see, the problem we have solved. Now I'm just taking it a little bit further to show you something else. Now this can be written as lambda square. There is no lambda square here, there is no lambda square here, so 0, 0. Here there is no lambda square, here you have lambda square. No lambda square, no lambda square, no lambda square, lambda square. Yes. Plus, now we can write only for lambdas. So minus 14 lambda, 2 lambda, 3 lambda, 4 lambda, minus 10 lambda, 6 lambda, 7 lambda, 8 lambda, minus 6 lambda. And we can further write the constants. So that would be minus 3, 6, minus 3, 6, minus 12, 6. Then we have minus 3, 6, minus 3. Okay. So this would be, again we can write this as lambda square 1, 0, 0, 0, 1, 0, 0, 0, 1. Plus lambda we can take it out and write it as minus 14, 2, 3, 4, minus 10, 6, 7, 8, minus 6. And this remains as it is because these are constants. 3, 6, minus 3, 6, minus 12, 6, minus 3, 6, minus 3. Now what we can do is, we can write this as, let's say, B0. This we can write it as B1, and we can write this as B2. So we can write this as B0 lambda square plus B1 lambda plus B2. Since it's a matrix, let's write it as I, because we don't want to convey the idea that this is a normal variable. We want to show it is actually a matrix. So here B0, B1 and B2 are matrices, which are functions of elements of A, right? These are all elements of A. So A31 is a function of elements of K. So that means what? This is nothing but a polynomial where we have coefficients as matrices. So therefore matrix polynomial. Yes. So this is very important. In the next session, when we look at Cayley-Hamilton theorem, we will be utilizing this form. So I think you got the idea. But let's look at some properties of the adjoint. Okay. A times the adjoint of A is equal to adjoint of A times A is equal to the determinant of A times I, the identity matrix. Okay, second one is the determinant of adjoint of A is equal to the determinant of A to the power of n minus 1. Now here A, matrix A is invertible square matrix. Third one is adjoint of A is equal to the determinant of A to the power of n minus 2. Fourth one is adjoint of A times B. The product of two matrices is going to be adjoint of B times adjoint of A. So kind of a reversal. Okay. Fifth one, adjoint of A transpose is going to be the adjoint of A transpose. Finally, sixth one is adjoint of a scalar multiple of A is equal to k to the power of n minus 1 times adjoint of. So you need to be aware of these properties. In our next session, we are going to use this particular property. So I think that's enough for today. Bye.